Richard Feynman's first and most radical idea about time begins with a simple but unsettling claim. Time is not an independent river flowing through the universe. It is a human way of describing change. This idea sounds almost too simple at first, yet it quietly dismantles centuries of assumptions. Most people grow up believing that time exists on its own, ticking away whether anything happens or not. We imagine it as something real and physical, like space or matter. Feynman questioned this instinct directly. He argued that if absolutely nothing in the universe changed, no motion, no vibration, no decay, no interaction, then the idea of time would lose all meaning. Without change, there is nothing to compare, and without comparison, time cannot be defined. To understand this, Feynman often returned to how time is actually measured. When we say a second has passed, what do we really mean? We do not capture time itself in a container. We observe a process. A pendulum swings back and forth. A quartz crystal vibrates. Cesium atoms oscillate between energy states. These motions repeat, and we count those repetitions. We then agree, collectively, to call a specific number of repetitions a second. The crucial point is that we are not measuring time. We are measuring motion and labeling it as time. Time, in this sense, is a bookkeeping system, not a substance. This realization changes how we interpret everyday experience. When someone says time is passing slowly or quickly, they are really commenting on the rate of change they are experiencing. In moments of boredom, when little changes around us, time feels slow. In moments of excitement, when many things change rapidly, time feels fast. The clock does not change its pace, but our perception of change does. Feynman saw this not as a psychological trick, but as evidence that time is deeply tied to processes, not to an invisible flow. Historically, this idea clashes with the classical picture introduced by Isaac Newton. Newton believed time was absolute, flowing uniformly throughout the universe, independent of anything happening within it. According to that view, time existed even if the universe were empty. Feynman respected Newton's genius, but pointed out that modern physics no longer supports this assumption. Experiments and theories show that time cannot be separated from physical events. It bends, stretches, and even slows down depending on motion and gravity. This alone suggests that time is not an independent background, but a property emerging from how matter and energy behave. Feynman's approach was always grounded in operational thinking. He believed that if you cannot explain how something is measured, you do not fully understand it. When applied to time, this principle becomes powerful. Every method we have for measuring time depends on physical change. Even the most accurate atomic clocks rely on transitions within atoms. If atoms somehow stopped changing, clocks would stop. Without clocks, the concept of time collapses. This is not just a technical limitation. It is a philosophical statement embedded in physics itself. Consider a universe frozen in perfect stillness. No particles move, no fields fluctuate, no light travels. In such a universe, asking how much time has passed becomes meaningless. There is no earlier or later because there is no difference between states. Feynman used this kind of reasoning to show that time does not exist independently of events. It is not a thing that causes change. It is a way to describe change after it happens. This perspective also reframes how we think about the past and future. The past is not a location in time that still exists somewhere behind us. It is a record of changes that have already occurred. Memories, photographs, fossils, and radiation left over from the early universe are all physical traces. They are present objects encoding information about earlier states. The future, by contrast, does not yet exist in the same physical way because its changes have not happened. Time, then, is not a line we travel along, but a sequence of states the universe moves through. Feynman was careful not to oversimplify. He did not claim time is an illusion or that it does not exist at all. Instead, he argued that time exists as a relationship between events. It is real in the same way distance is real. Distance does not exist without objects to be separated. Similarly, time does not exist without events to be ordered. We do not ask how far apart two empty points are if nothing occupies them. In the same way, asking how much time passes without any change is meaningless. This view becomes even more important when we look at modern physics. In relativity, time behaves differently depending on motion and gravity. A fast, moving clock runs slower than a stationary one. A clock closer to a massive object runs slower than one farther away. These effects are not errors or malfunctions. They are consequences of how spacetime works. If time were an independent, universal flow, such differences would not occur. The fact that they do occur strongly supports Feynman's idea that time is not separate from physical processes. Feynman often emphasized that our language misleads us. We talk about time as if it were something that passes or flows, but these are metaphors borrowed from motion. Ironically, we describe time using the very concept it is meant to measure. This circularity hides the truth. Nothing called time is flowing. What is flowing are particles, energy, radiation, and information. Time is the label we attach to the order and rate of these flows. This insight also affects how we think about aging and decay. We say things age because time passes, but in reality, things age because physical and chemical processes occur. Cells divide, molecules break, entropy increases. Time does not cause these processes, it describes them. If the processes stopped, aging would stop, regardless of how much time we think should pass. This reverses a deeply ingrained intuition and places causality back where it belongs, in physical interactions, not in time itself. In cosmology, this idea becomes even more striking. The early universe is often described as a moment in time, the beginning of everything. But from Feynman's perspective, the beginning of time is really the beginning of change. When the universe was in a hot, dense, rapidly evolving state, change was extreme, and time as a measure became meaningful. Asking what happened before the universe began is tricky, not because it is forbidden, but because the concept of before may lose meaning when there are no earlier physical states to compare. Feynman's approach avoids mystical explanations. He did not appeal to hidden dimensions of time or metaphysical flows. Instead, he insisted on clarity. If time is defined by change, then understanding time means understanding the laws that govern change. This shifts the focus from abstract speculation to concrete physics. It encourages us to study motion, energy, entropy, and information rather than chasing an invisible entity. This way of thinking also explains why time feels so important in human life. Our bodies and minds are systems constantly changing. Memories accumulate, bodies grow and decay, experiences alter brain states. Because we are embedded in change, time feels fundamental. But this feeling does not mean time is a substance acting upon us. It means we are deeply aware of change because our survival depends on tracking it. Feynman's idea challenges the emotional weight we give to time. People fear running out of time, losing time, or wasting time. From his perspective, what we are really afraid of is losing opportunities for meaningful change. Time itself does not take anything away. Physical processes do. choices do, entropy does. Understanding this does not remove the emotional reality, but it grounds it in the physical world. At its core, this keynote teaches humility. It reminds us that some concepts we treat as fundamental may actually be derived. Time feels basic because it is woven into every experience, but physics suggests it emerges from deeper rules. Feynman did not claim to have the final answer, but he showed a path forward. Stop asking what time is in isolation and start asking how change happens and how we measure it. By reframing time as a description rather than a driver, Feynman gave us a cleaner, more honest picture of reality. The universe does not move because time pushes it forward. The universe changes according to physical laws, and we call that sequence of change time. This idea, once fully absorbed, quietly transforms how we see clocks, history, aging, and even our own lives. It does not make time disappear, but it places it exactly where it belongs, not as a master of the universe, but as a map we use to understand its motion. Richard Feynman's second keynote idea about time pushes the discussion deeper by shifting attention away from abstract philosophy and firmly into the working machinery of physics. For him, time could never be understood by sitting back and thinking about it in isolation. It had to be understood by watching what nature actually does. Motion, probability, and physical laws were the only honest guides. Any explanation of time that did not connect directly to how particles move, interact, and obey equations was, in his view, incomplete. Feynman believed that the universe does not consult a clock before deciding how to behave. Particles do not wait for time to pass before they move. They move according to forces and probabilities. Time appears in the equations of physics not as a commanding authority, but as a parameter that helps us track change. When a particle moves from one place to another, when energy transfers, when a wave oscillates, we use time to describe how quickly or slowly these processes occur. But the driving force is always the physical law, not time itself. In classical physics, motion is described using time as a variable. An object has a position at one moment and a different position at another. Velocity is change of position with respect to time. Acceleration is change of velocity with respect to time. This mathematical structure can make it seem as though time is doing something active. Feynman warned against this misunderstanding. Time in these equations is not pushing objects forward. It is simply a reference scale that allows us to compare one state of motion with another. What made Feynman's view powerful was his insistence that physics should remain operational. If time plays a role in an equation, we should be able to point to a physical process that corresponds to it. When we say an event takes 5 seconds, we are really saying that during that event, a certain number of standard motions occurred elsewhere, such as oscillations in a clock. Motion is always compared to motion. Nothing ever compares itself to time directly. This becomes even clearer in quantum mechanics, where Feynman made some of his most important contributions. At the quantum level, particles do not behave like tiny billiard balls moving along clear paths. Instead, they are described by probabilities. A particle does not have a single definite path from one point to another. According to Feynman's formulation, it explores all possible paths. Each path contributes to the final outcome with a certain probability amplitude. In this picture, time does not act like a steady conveyor belt. Instead, it is part of the mathematical framework that allows probabilities to evolve. The future state of a system is not determined with certainty, but with likelihoods. The laws of physics tell us how these likelihoods change. Time, once again, is not the cause of change, but the label we use to track how probabilities shift. One of the most striking aspects of Feynman's quantum work is that many of the fundamental equations do not strongly prefer a direction of time. If you reverse time in the equations, they often still work. A particle moving forward in time according to the equations could also be described as moving backward in time with certain adjustments. This deeply challenges the everyday intuition that time has an obvious, built-in direction. Feynman did not see this as a flaw. He saw it as a clue. It suggested that the arrow of time we experience is not rooted in the basic laws themselves, but in how complex systems behave statistically. At the microscopic level, the rules are flexible. At the macroscopic level, probability takes over. When trillions upon trillions of particles interact, certain outcomes become overwhelmingly more likely than others. This is where time begins to feel directional. Motion, in Feynman's view, is the key to understanding this transition. Individual particles follow probabilistic rules, but large collections of particles tend to move from less probable arrangements to more probable ones. This tendency gives rise to irreversibility. A drop of ink spreads out in water, but it never spontaneously gathers itself back together. The laws governing the molecules allow both processes in principle, but probability overwhelmingly favors one direction. Time enters the picture here as a way to describe this unfolding of probability. We say the ink spreads as time passes, but what we really mean is that the system evolves from an unlikely state to a more likely one according to physical laws. Time is the coordinate we attach to this evolution. The deeper cause lies in statistics and motion, not in time itself. Feynman often emphasized that nature does not care about our intuitions. The universe does not organize itself to match human feelings about past, present, and future. Instead, it follows precise mathematical rules. These rules are simple at the fundamental level, yet their consequences become incredibly rich and complex when many particles interact. Time, as we experience it, emerges from this complexity. This perspective also explains why certain processes appear irreversible even though the underlying laws are reversible. Breaking a glass, burning fuel, aging, and decay all feel like one-way journeys through time. But at the level of individual atoms, the equations do not forbid the reverse. The reason we never see the reverse is not that time forbids it, but that probability makes it unimaginably unlikely. Feynman found this distinction crucial. Confusing time with probability leads to misunderstanding. In his teaching, Feynman often stripped away grand language and replaced it with concrete examples. He would describe particles bouncing, waves interfering, atoms vibrating. Time was always present in the description, but never as a mysterious force. It was simply part of the bookkeeping. This approach demystified time without diminishing its importance. On the contrary, it made time more interesting by tying it directly to how the universe actually works. Another important aspect of Feynman's view is that time cannot be separated from measurement. In quantum mechanics, measurement itself plays a strange role. Observing a system affects it. Probabilities collapse into outcomes. Time is involved in this process, but again, it is not acting alone. The interaction between the measuring device and the system is what produces change. Time is how we describe when that interaction occurs and how long it lasts. Feynman resisted attempts to give time a special metaphysical status. He was skeptical of explanations that treated time as something fundamentally different from other physical quantities. To him, time was deeply connected to energy, motion, and action. In fact, in physics, time and energy are linked in a precise mathematical way. This relationship shows that time is woven into the structure of physical law, not floating above it. By focusing on motion and probability, Feynman also highlighted the limits of human intuition. Our brains evolved to deal with slow, moving, large-scale objects. At that scale, time feels smooth, continuous, and obvious. But when we look closely at nature, that smoothness dissolves into fluctuations and uncertainty. Time does not vanish, but it loses its familiar shape. This realization has profound implications. It suggests that any final theory of reality will not explain time by elevating it to a cosmic ruler. Instead, it will explain time by showing how it arises from deeper rules governing motion and interaction. Feynman was comfortable living with this incomplete picture. He believed that admitting uncertainty was more honest than inventing comforting stories. Ultimately, this keynote teaches a disciplined way of thinking. Instead of asking what time means in an abstract sense, Feynman encourages us to ask how physical systems evolve and how we describe that evolution. Time becomes a lens rather than an engine. It helps us see patterns in motion and probability, but it does not create those patterns. Through this lens, time stops being a mysterious enemy racing against us. It becomes a record of how nature behaves according to its laws. Motion happens, probabilities shift, structures form and dissolve. We observe these changes and organize them using time. That, for Feynman, is not a disappointing answer. It is a powerful one, because it ties one of the most profound human experiences directly to the measurable, testable behavior of the universe itself. Richard Feynman's third keynote about time moves into territory where everyday intuition completely breaks down. Here, time is no longer the steady, universal rhythm people experience in daily life. At the quantum level, time behaves in ways that feel unfamiliar, indirect, and sometimes almost unreal. Feynman never claimed that time disappears in the quantum world, but he showed that it stops behaving like a simple, universal clock shared by everything in the universe. In ordinary life, time feels uniform. 1 second here feels the same as 1 second anywhere else. This intuition comes from our experience at low speeds and weak gravitational fields. Quantum physics, however, deals with scales where particles are incredibly small and energies can be extreme. In this realm, the neat separation between objects, motion, and time begins to blur. Feynman's work revealed that the rules governing tiny particles treat time very differently from how human intuition expects. One of the most striking insights comes from the mathematical structure of quantum mechanics itself. Many of its core equations are symmetrical with respect to time. If time is mathematically reversed, the equations often remain valid. This implies that, at a fundamental level, nature does not strongly prefer a single direction of time. The forward march of time that humans experience is not written boldly into the deepest laws of physics. Instead, it seems to arise from something else. Feynman was deeply interested in this contrast. On one hand, everyday life feels irreversible. Glasses break, but they do not unbreak. People age, but they do not grow younger. On the other hand, the equations describing electrons, photons, and atoms do not forbid these processes from running backward. This tension suggests that the direction of time is not a basic rule of the universe, but an emergent feature that appears only when many particles interact together. At the quantum level, particles behave more like waves of probability than solid objects. They do not have exact positions or paths until they interact with something. Instead, they exist in a range of possible states. Time in this context acts more like a parameter that tracks how these probabilities evolve. It does not dictate what must happen. It describes how likelihoods change. Feynman's path integral formulation makes this idea especially vivid. According to this approach, a particle traveling from one point to another does not choose a single path. It explores all possible paths simultaneously. Each path contributes to the final outcome, and the observed behavior emerges from the combination of all these possibilities. Time in this picture is not a single straight line. It is woven into countless potential histories that overlap and interfere with one another. This leads to a strange but powerful conclusion. At the quantum level, the distinction between past and future becomes less absolute. The equations allow particles to behave in ways that, from a classical perspective, look like influences traveling backward in time. Feynman was careful to explain that this does not mean particles literally send messages to the past. Rather, it shows that our classical intuition about time as a rigid sequence of events does not fully apply at microscopic scales. Another key aspect of quantum time is uncertainty. Just as there is uncertainty in position and momentum, there is a deep connection between time and energy. Short-lived states have uncertain energies, and precise energies correspond to long-lived states. This relationship is not a limitation of our instruments. It is built into the structure of reality. Time, therefore, cannot always be sharply defined at the quantum level. Events do not always happen at precise moments in the way we imagine. Feynman used this to challenge the idea that the universe runs like a perfectly synchronized clock. At small scales, nature is noisy and probabilistic. Processes happen with certain chances over intervals rather than at exact instants. Time becomes fuzzy, not because our measurements are poor, but because reality itself does not assign exact timestamps to every event. This fuzziness does not disappear when particles interact. Instead, it becomes hidden beneath layers of complexity. When enormous numbers of particles come together, their individual uncertainties average out. The result is the smooth, predictable flow of time we experience in everyday life. From Feynman's perspective, classical time is not fundamental. It is a large-scale approximation that emerges from quantum behavior. This insight helps explain why attempts to unify quantum mechanics with gravity are so challenging. Gravity, as described by general relativity, treats time as something flexible and geometric, shaped by mass and energy. Quantum mechanics treats time as a parameter governing probability evolution. These two pictures do not easily fit together. Feynman recognized this tension and saw it as a sign that our understanding of time is still incomplete. He resisted simple answers. Instead of claiming that time is an illusion or that it does not exist, he emphasized that time behaves differently in different contexts. At the quantum level, it loses the absolute authority it seems to have in daily life. It becomes intertwined with measurement, interaction, and uncertainty. Measurement plays a particularly strange role in quantum time. When a quantum system is measured, its range of possibilities collapses into a specific outcome. This collapse appears to happen at a particular moment, yet the theory itself does not clearly define when that moment occurs. Time here is tied to interaction, not to an independent ticking clock. The act of measurement creates a boundary between before and after, giving time a localized meaning. Feynman was honest about the mystery here. He did not pretend to know exactly how measurement works at the deepest level, but he was clear about what the mystery tells us. Time is not a simple, universal backdrop. It is deeply connected to how systems interact and exchange information. This connection to information is crucial. At the quantum level, information about a system is limited and fragile. Time becomes a way of tracking how information spreads, transforms, and sometimes disappears. The future is uncertain not because time hides it, but because the laws of physics allow multiple outcomes. Time is the stage on which uncertainty plays out, not the force that resolves it. Feynman's perspective also helps explain why quantum effects rarely feel like time travel in everyday life. Although the equations allow time, symmetric behavior, the sheer number of particles in macroscopic objects overwhelms these effects. Quantum coherence breaks down and classical order emerges. Time regains its familiar direction, not because the laws changed, but because probability became decisive. This view removes much of the mysticism surrounding time at small scales while preserving its wonder. Time is not a magical dimension where anything can happen. It is a concept shaped by the rules governing matter and energy. At the quantum level, those rules allow flexibility, symmetry, and uncertainty. At the human level, they produce stability, direction, and memory. By exploring time in the quantum world, Feynman revealed how deeply our everyday experience depends on scale. What feels absolute and obvious is, in fact, contingent and emergent. Time is real, but its character changes depending on how closely we look. The deeper we go, the less it resembles the simple ticking clock we carry in our pockets. This keynote ultimately teaches restraint. It warns against projecting human intuition onto realms where it does not belong. Time behaves strangely at the quantum level not because nature is confused, but because our expectations are. Feynman invited us to accept this strangeness without fear, to see it as evidence that reality is richer than common sense suggests. In this view, time is not broken or incomplete at the quantum level. It is simply different. It operates as a flexible parameter governing probabilities rather than as a rigid ruler marking moments. From this foundation, the familiar flow of time emerges, not as a fundamental law, but as a collective effect of countless quantum interactions working together. Richard Feynman's fourth keynote about time focuses on a question that feels simple, but reaches deep into the foundations of physics and human experience. Why does time seem to move in only one direction? Why do we remember the past but not the future? And why do causes come before effects? Feynman approached this not as a mystery of time itself, but as a consequence of how the universe organizes events, information, and matter. In his view, the direction of time does not come from clocks, calendars, or some built-in cosmic arrow. It comes from cause and effect, shaped by probability and the growth of disorder. In everyday life, the direction of time feels obvious. You drop a glass, it shatters. You never see the pieces leap up and reassemble themselves into a perfect glass. You remember yesterday, not tomorrow. This way character of experience is so deeply ingrained that many people assume time itself must be responsible. Feynman challenged this assumption. He argued that time does not force events to happen in one direction. Instead, physical processes unfold in ways that make one direction overwhelmingly more likely than the other. At the heart of this idea lies the concept of cause and effect. Causes precede effects, not because time commands them to, but because the physical laws governing interactions work that way. When two particles collide, their future motion depends on their present state. The equations use current conditions to predict what happens next. They do not use future conditions to determine the present. This logical structure gives events an order. We label that order using time. Feynman emphasized that this ordering is closely tied to information. The past leaves records, the future does not. Footprints in sand, memories in brains, marks on paper, radiation traveling through space. All of these are physical traces of earlier events. They exist now, encoding information about what has already happened. The future, by contrast, has not yet produced such records. This asymmetry makes the past accessible and the future uncertain, reinforcing our sense of time's direction. Crucially, this is not because the laws of physics forbid future records. It is because creating records requires energy, structure, and order. Writing information, storing memory, or leaving traces all involve physical processes that increase overall disorder elsewhere. This brings in the role of entropy, a concept Feynman often used to clarify the arrow of time. Entropy is a measure of how many microscopic arrangements correspond to a macroscopic state. Highly ordered states are rare and specific. Disordered states are common and numerous. When systems evolve, they tend to move from less probable, more ordered arrangements to more probable, disordered ones. This tendency is statistical, not absolute. The laws of physics allow entropy to decrease locally, but the odds are astronomically against it happening on a large scale. Feynman stressed that entropy, not time itself, gives events their irreversible character. When a glass breaks, it shatters into many pieces because there are vastly more ways for the atoms to be arranged as broken shards than as a perfectly intact glass. The reverse process is not forbidden by physical law, but it is so improbable that it effectively never happens. We experience this statistical inevitability as the forward flow of time. This explains why cause and effect feel aligned with time. Causes are associated with lower entropy states, effects with higher entropy states. We prepare conditions, and outcomes follow. The preparation requires careful arrangement and energy. The outcome disperses energy and increases disorder. Time, in this sense, is a label for the direction in which entropy increases. Feynman was careful to point out that entropy does not require consciousness or intention. The universe does not choose to increase disorder. It simply follows probability. When many particles interact, certain outcomes dominate. The direction of time we experience is the direction in which the universe naturally evolves due to overwhelming statistical weight. This idea also explains why memory works the way it does. Memories are physical records stored in the brain. Creating and maintaining those records requires energy and increases entropy in the surrounding environment. You can remember yesterday because your brain formed stable patterns in response to past events. You cannot remember tomorrow because those patterns have not been formed yet. The asymmetry of memory is not psychological magic. It is thermodynamics. Feynman extended this reasoning to larger scales. The universe itself appears to have started in a state of extremely low entropy. Matter and energy were arranged in a highly ordered way. From that beginning, entropy has been increasing. Stars form, burn fuel, and spread energy into space. Galaxies evolve. Structures form and decay. This overall increase in entropy gives the universe a clear direction of evolution. Time, as we experience it, is aligned with this cosmic trend. Importantly, Feynman did not claim to know why the universe began in such a low entropy state. He admitted this as a deep open question, but he insisted that once you accept that starting point, the arrow of time follows naturally. You do not need to invent a special property of time itself. Cause and effect, memory, and irreversibility all emerge from statistical behavior. This view also clarifies why fundamental physics often appears time-symmetric. At the level of individual particles, the equations do not care whether time runs forward or backward. But when you scale up to systems with enormous numbers of particles, symmetry breaks down in practice. Not because the laws change, but because probability dominates. Feynman found this distinction essential. Confusing microscopic reversibility with macroscopic irreversibility leads to endless confusion about time. Another important insight is that causality is local. Causes produce effects through interactions. There is no global cosmic clock enforcing order. Events influence near-by events, and chains of influence spread through space. Time emerges from this network of causal connections. Where there is no interaction, there is no meaningful sense of before and after. This perspective also reshapes how we think about determinism. Even in a universe governed by probabilistic laws, cause and effect still hold. A cause does not guarantee a specific effect, but it shapes the range of possible outcomes. Time organizes these possibilities into sequences. The future is open not because time is mysterious, but because probability allows multiple paths forward. Feynman often warned against romanticizing time. He disliked explanations that treated time as a force dragging everything forward. Such language hides the real mechanisms at work. When something happens, it is because particles interacted according to physical laws, not because time decided it was their turn. Understanding this can be unsettling. It removes the idea that time is a guiding river carrying us along. Instead, we are inside a universe constantly rearranging itself according to probability. Time is our way of describing the order of those rearrangements. Yet Feynman also found this view liberating. It replaces vague mystery with concrete understanding. The direction of time is not an unsolvable riddle. It is a natural outcome of how matter behaves in large numbers. This does not make time less meaningful. It makes it more deeply connected to the physical world. This keynote ultimately reveals that time's arrow is not carved into the universe at the deepest level. It emerges from cause and effect, memory and entropy. We experience time moving forward because the universe, starting from an ordered state, naturally evolves toward disorder. Our lives, our histories, and our expectations are embedded in that process. In this light, time is not a tyrant enforcing decay, nor a mystical force shaping destiny. It is a measure of how causes give rise to effects in a universe ruled by probability. Feynman's insight strips away illusion without stripping away wonder. It shows that the one-way nature of time is not imposed from outside, but grows organically from the way the universe is built. Richard Feynman's fifth keynote about time brings all the earlier ideas together into a final, deeply human insight. Truly understanding time requires humility, curiosity, and acceptance of uncertainty. For Feynman, time was not a puzzle to be conclusively solved and put away. It was an invitation to think more clearly, to question assumptions, and to remain comfortable with not knowing everything. He believed that the greatest danger in science was not ignorance, but the illusion of certainty. Throughout his work, Feynman emphasized that physics does not tell us what reality is. In some ultimate philosophical sense, it tells us how nature behaves and how accurately our models predict observations. Time, like many fundamental concepts, sits at the edge of what our theories can fully explain. We can describe how time behaves under motion, gravity, and quantum uncertainty, but we do not possess a final definition that satisfies every question. Feynman saw this not as a failure, but as an honest reflection of how science progresses. One of his most important lessons was the distinction between knowing a name and understanding a thing. People can define time in poetic or technical language, but that does not mean they understand it. True understanding comes from seeing how time appears in experiments, equations, and measurements, and from recognizing the limits of those tools. Feynman encouraged students and audiences to resist the temptation of comfortable explanations that sound deep but explain little. Humility plays a central role here. Time feels intimate and familiar because it shapes every human experience. That familiarity can deceive us into thinking we understand it more deeply than we do. Feynman warned against trusting intuition too much, especially when dealing with concepts that evolved far outside the environment in which human intuition developed. The universe is under no obligation to make sense in human terms. This humility extends to the recognition that different theories treat time differently. In classical mechanics, time is a simple parameter. In relativity, it becomes flexible and intertwined with space. In quantum mechanics, it acts as a parameter governing probability, yet resists full integration with measurement and gravity. These differences suggest that our current picture is incomplete. Any future theory that unifies these frameworks may change our understanding of time in ways we cannot yet imagine. Feynman was comfortable living in this incomplete picture. He often said that uncertainty is not a weakness of science, but its strength. It keeps inquiry alive. With time, this attitude is essential. Every attempt to declare the final nature of time risks closing off questions that have not yet been asked. Curiosity, for Feynman, was the engine that drove understanding forward. Instead of asking grand metaphysical questions about time, he preferred asking precise, answerable ones. How does a clock behave when it moves? How does gravity affect the rate of time? How do quantum probabilities change over short intervals? Each of these questions deepens understanding without pretending to solve the ultimate mystery. This approach also guards against misuse of scientific ideas. Time travel, paradoxes, and sensational claims often arise from taking mathematical tools too literally or ignoring their limits. Feynman believed that respecting uncertainty helps prevent such errors. Just because equations allow certain interpretations does not mean nature permits them in practice. Careful reasoning and experimental evidence must always guide conclusions. Another key aspect of this keynote is the idea that time is not separate from our role as observers. All measurements of time involve interaction. A clock must interact with its environment. An observer must compare events. These interactions are physical processes subject to uncertainty and limitation. There is no view from outside the universe where time can be observed in its entirety. We are always inside the system we are trying to understand. Feynman found this deeply meaningful. It meant that understanding time also means understanding our place in the universe. We are not detached spectators watching time flow past. We are participants in the processes that give time meaning. Our memories, measurements, and theories are all part of the same physical world they describe. This realization encourages intellectual honesty. When physicists say they do not fully understand time, they are not admitting defeat. They are acknowledging the complexity of reality. Feynman admired this honesty and practiced it himself. He openly admitted when something was confusing or unresolved. In his view, pretending to understand what we do not is far worse than admitting uncertainty. Acceptance of uncertainty also has a practical side. It allows theories to evolve. New experiments may reveal behaviors that challenge existing models. When that happens, clinging to rigid definitions of time can slow progress. Remaining flexible allows science to adapt and refine its understanding. Feynman's attitude toward time also reflects a broader philosophy of science. Science is not about collecting unquestionable truths. It is about building models that work, knowing they may later be replaced by better ones. Time, as described by physics today, is part of such a model. It works extremely well in many contexts, but it may not be the final word. This humility does not diminish the power of scientific knowledge. On the contrary, it strengthens it. Technologies like GPS, atomic clocks, and particle accelerators depend on precise understanding of how time behaves under specific conditions. These successes show that even incomplete theories can be extraordinarily effective. At the same time, Feynman warned against confusing practical success with ultimate understanding. Being able to calculate time dilation does not mean we know what time fundamentally is. Recognizing this gap keeps curiosity alive. There is also a deeply human message in this keynote. People often feel anxiety about time, about its passing, its limits, and its irreversibility. Feynman's perspective does not offer comfort through illusion. Instead, it offers clarity. Time is not an enemy counting down our lives. It is a description of how the universe changes, and we are part of that change. Accepting uncertainty can be freeing. It shifts focus from controlling time to engaging meaningfully with change. We cannot stop entropy or reverse causality, but we can understand them. Understanding does not grant power over time, but it grants perspective. Feynman believed that wonder survives uncertainty. In fact, it depends on it. If time were fully understood and neatly explained, it would lose much of its fascination. The unanswered questions keep science vibrant and human curiosity alive. In the end, this keynote reminds us that time is not just a scientific concept. It is a meeting point between physics, experience, and humility. Feynman did not offer a final definition of time, and he never claimed to. What he offered instead was a way of thinking rigorous, honest, curious, and open-ended. Through that way of thinking, time becomes less of a riddle demanding a final answer and more of a landscape to explore. Each discovery reveals new questions. Each explanation exposes deeper layers. That, for Feynman, was not a problem to be solved, but the true beauty of understanding the universe.